Okay, so to answer this question, it's actually better if we first examine another group with the group known as SU2. And we'll find that this group is very closely related to SO3. Okay? So next I want to discuss SU2, and that will naturally lead us to identify the parameter space of SO3, because we'll see that there exists a homomorphism between SU2 and SO3, okay? Okay, so what is SU2? So to motivate this, I'm going to go to quantum mechanics a little bit. So this doesn't mean you have to know quantum mechanics. You don't need to know quantum mechanics. I'm just introducing this as a way to motivate SU2. Okay, so in quantum mechanics, the state of a physical system is described by a complex valued wave function. That wave function is usually noted as psi, and it's a function of space and time. Okay? So all observables are somehow derived from the probability density P, which is psi star psi. Okay, so this is the probability density. So for example, if I have some observable O, which is a Hermitian operator, I want to compute its expectation value, then what we do is that we then express it in some position basis, and then it has some eigenvalue spectrum, and we basically multiply it with the momentum and integrate it, very roughly speaking. Sorry, not momentum, the probability. Okay, so what I'm trying to say is that this is something of central importance. But for particles, such as an electron, just the wave function is not enough. Such particles, such as spin half particles, have what is known as a spin degree of freedom, and such spinners, as they're called, are described by a matrix, a two-component matrix wave function. Okay. So you have some two-dimensional matrix, and it has psi 1 and psi 2. Okay. And in this case, the probability density is described by this big psi dagger, big psi, which of course is small psi 1, star psi 1 plus psi 2 star psi 2. Okay. So now the group of transformation and that leave, psi dagger of psi invariant is U. Suppose we are just denoting it by U. So if I have psi and I change it to say psi prime, which is related to some matrix U acting on psi. So this is a 2x2 complex matrix, right? Why is it complex?
Because the Hilbert space has the complex numbers as its field.
Right. So basically these guys are complex. So this has to be in general complex. So if you want this to be invariant, then we get U acting on psi dagger, U acting on psi, and then I get psi, sorry, my handwriting is going down the hill. It's psi, U dagger. This is dagger, U of psi. So if this thing, so this has to be equal to psi dagger of psi. And that can only happen if U dagger U is 1 or U of dagger is equal to U inverse. Okay, such matrices are called unitary matrices. Okay, so matrices which satisfy this condition, they're called 2x2. They're called the U2 group, not the band, the U2 group. So the U2 group consists of 2x2 unitary matrices, okay? But in quantum mechanics, suppose you have a wave function which is normalized, which means that, if you take this and you integrate over all space, it'll give you 1. But even then, the wave function is not completely specified. In quantum mechanics, a normalized wave function can be multiplied by a constant phase, and this phase does not change its normalization, right? Because here it drops out, right? Do you agree? So do you agree that in quantum mechanics, this physical state and this state is the same?
Yes.
Yeah, the e to the I5 multiplies with e to the minus I5. And
right. So in quantum mechanics, we always have this freedom to multiply a wave function by phase. And what happens with U2 matrices is that a U2 matrix can be written in terms of a phase times another matrix where V has this condition, the determinant of V is 1. So using this freedom of quantum mechanics, we can set U to be equals to V. That is, we can set the e to the power I phi to 1, this phase factor to 1, because it has no physical significance. You know, this transformation that we did, this U can be written as e to the power I phi times B, but this guy has no significance. So we might as well just, you know, set this to 1. Because of this fact that, you know, in quantum mechanics, okay. So in essence, the group of transformation, so in essence, the group of matrices, or the group of non-trivial transformations, that keep this thing invariant is SU2. The S means its determinant is 1. So SU2 matrices are matrices which are unitary and their determinant is 1. Okay. So this is the definition of the SU2 group.
Sir, SU means special unitary, right?
Yes.
So how did we arrive at the condition that the determinant must be 1?
Because the phase, we said the phase part, we are ignoring the phase part. We are saying that we can use this freedom in quantum mechanics to set this to a specified value, say 1.
But does that fix the determinant?
Yes, so if you look at this determinant of U is some phase. So if you look at, say, the U dagger U equals to 1, the original condition we had, and if you take the determinant of that, then we have determinant of U dagger, determinant of U is 1. So what is the determinant of this, you know,
So it means that the magnitude of the determinant of U is 1. So in general, it can be any phase.
Yeah,
so,
exactly. Yeah, that's the whole point.
Oh, okay.
So
So we're just
we
fixing
are
the
fixing
phase
the
to
phase.
1.
Yeah.
All
The
right.
magnitude, yeah. We are saying that the phase of the determinant doesn't matter. Okay.
Okay, sir.
Yeah.
So SU2 basically comes from this physical consideration, right? We go
Yeah.
to, okay.
Otherwise, it would just be unitary.